Structure determination of organometallic compounds is crucial for understanding the reactivity of a given molecule. Various models and techniques enable scientists to elucidate compounds in question, as for example, ferrocene. Ferrocene, an organometallic compound, was first reported by Keeley and Pawson in 1951. They proposed a structure consisting of an iron atom with 2 single bonds to 2 carbon atoms on separate cyclopentadiene rings. However, Wilkinson and Woodward suggested an alternative for the ferrocene structure in which the iron atom is sandwiched between 2 cyclopentadiene rings with equal binding to all 10 carbon atoms. The structure proposed by Wilkinson has since been confirmed by X-ray crystallography and proton NMR. This video will illustrate the 18-electron rule to predict the structure of organometallic complexes, the synthesis of ferrocene, its spectroscopic and electrochemical analysis, and some of its applications. When proposing molecular structures, always consider the amount of valence shell electrons. Main group elements can accommodate up to 8 electrons, while transition metals can contain up to 18 electrons in its valence shell. Transition metals have 9 valence orbitals, 1s, 3p, and 5d orbitals, with 2 electrons in each. With some exceptions, transition metal complexes with 18 valence electrons are highly stable compounds. To determine the total electron count of a transition metal complex, 2 models can be used, the ionic or the covalent method. Both methods utilize the same ligand classifications. X-type ligands include anionic groups such as halides, hydroxide, or alkoxide. L-type ligands include lone pair donors, such as amines and phosphines. And Z-type ligands are neutral Lewis acids, which are electron pair acceptors. To demonstrate the 2 models, let's use triamine trichlorocobalt-3 as an example. Consider the cobalt atom, which is in group 9 of the periodic table and has 9 valence electrons. Since the oxidation state of the cobalt in this complex is +3, the total number of valence electrons contributed is 6. The X-type ligands, being the 3 chlorides, and L-type ligands, the 3 amines, contribute a total of 12 electrons, while Z-type ligands are not available, yielding a total of 18 electrons. In the covalent model, the cobalt oxidation state is ignored and the molecule is not ionic, resulting in 9 electrons total. X-type ligands donate 1 electron, L-type ligands donate 2 electrons, and Z-type ligands, if present, contribute none, also yielding a total of 18 electrons. The counting of total electrons in ferrocene is more complex. The iron atom contributes 8 valence electrons, while the cyclopentadiene rings are classified as L2 X-type ligands, providing 5 electrons each, which come from the 2 double bonds and a radical, resulting in a total of 18 electrons. Whereas Pawson's original proposed structure would result in only 10 electrons because of the single-bonded cyclopentadienes. Now that we have discussed the principles of structure determination, let's synthesize ferrocene and identify which structure is correct. In a fume hood, add a stir bar and 50 milliliters of dicyclopentadiene to a clamped 100 milliliter round-bottom flask. Then attach the round-bottom flask to a distillation apparatus and place it in an oil bath, with the receiving flask in an ice bath. Set the hot plate to 160 degrees Celsius and stir gently. Fractionally distill approximately 5 milliliters of the cyclopentadiene monomer, which must be kept cold. Add to a 200 milliliter Schlenk flask labeled A a stir bar and freshly ground potassium hydroxide. Next, add 30 milliliters 1,2-dimethoxyethane. Attach the flask to a nitrogen line and fit with a rubber septum. While stirring under a nitrogen atmosphere, add to the solution 2.75 milliliters of cyclopentadiene via syringe and stir for at least 10 minutes. In a separate 200 milliliter Schlenk flask labeled B, add ground iron 2 chloride tetrahydrate and 12.5 milliliters of DMSO. Then fit a rubber septum attached to a nitrogen line and stir under a nitrogen atmosphere until all of the iron has dissolved. When this step is complete, insert either end of a double-tipped needle into each Schlenk flask and cannula transfer the iron solution to the cyclopentadiene solution dropwise over a 30-minute period. When the reaction is complete, pour the mixture into a beaker containing a slurry of 6 molar hydrogen chloride and 50 grams crushed ice and stir for a few minutes. Collect the resulting orange crystals by vacuum filtration on a fritted funnel. Wash precipitate with ice-cold water and then air dry. Purify the crystals by sublimation. Next, prepare an NMR sample of the purified ferrocene dissolved in chloroform D. Use the ATR attachment of the infrared spectrometer to obtain an IR spectrum. And lastly, collect a cyclic voltammogram of the ferrocene in acetonitrile at a scan rate of 100 millivolts per second. The NMR analysis shows a single peak at 4.17 ppm, which confirms that all of the hydrogen atoms are magnetically equivalent. Furthermore, the IR spectrum shows a single sp2ch stretch at 3096 reciprocal centimeters, confirming that the hydrogen atoms are equivalent and that the proposed Wilkinson structure is correct. Finally, let's take a look at the CV of ferrocene, which shows a single oxidation event. The E1/2 value can be calculated by taking the average of the cathodic peak potential and the anodic peak potential. In acetonitrile, the ferrocene-ferrocenium redox couple occurs at a potential of 90 millivolts. Now that we have discussed a procedure for preparing ferrocene, let's look at some of its applications. Palladium-catalyzed cross-coupling reactions are a valuable synthetic tool in the pharmaceutical industry. However, a common undesired side reaction is beta hydride elimination, which can be minimized with the use of 1,1-bisdiphenylphosphinoferrocene, or DPPF, as a chelating agent with palladium 2 chloride, forming 1,1-bisdiphenylphosphinoferrocene palladium 2 dichloride, abbreviated as DPPF-PDCl2. The suppression of beta hydride elimination and the high product yield has been attributed to the large bite angle of the DPPF ligand. With the advent of the catalyst, reactions such as the Suzuki coupling are possible and typically used to couple primary alkyl groups using 9-BBN reagents. The ease with which ferrocene can undergo electrophilic aromatic substitution, as in the Friedel-Crafts acylation or the formylation-Mannich reaction, has made it a promising source for organometallic drug candidates. These types of organometallic drugs have attracted interest due to their structural variety. For instance, M-arenes can support 3 functionalities, and M-carbenes can support 2. Currently, ferroquine, which contains elements of ferrocene and chloroquine, is undergoing evaluation as a commercial anti-malarial drug. Furthermore, ferrocephan, which is based on the elements of ferrocene and tamoxifen, is currently undergoing clinical trials as a potential breast cancer drug. Additionally, efforts are being made in developing nucleoside analogs of ferrocene in the study of DNA-RNA pathways. You've just watched Jove's introduction to the structure of ferrocene. You should now understand the 18-electron rule, the synthesis and characterization of ferrocene, and several of its applications. Thanks for watching.